Hello and welcome to the Embedded Online Conference, where I will talk about how to rapidly develop IoT devices. My name is Keil, I'm from Arm, and we have here a paper that we have developed together with AWS. So we will show how we connect IoT devices to AWS cloud services. The agenda of my speech is we will first run to the IoT endpoint support that Amazon offers with FreeRTOS libraries. I will give you a quick overview of the target devices that we are using. These are Arm Cortex-M microcontrollers. And then we will talk about the open approach for IoT on Cortex-M, where we will use CMSIS-Packs to deliver standard software components. We show various ways to implement secure internet communication. We show how you select and configure these software components for your application, and then how to optimize and validate the I/O interfaces of your application. Then I follow with reference examples for various evaluation kits, and I give you a demo on it, and then we have a summary where I basically summarize what we have talked about. The Amazon cloud solution is quite flexible. You see here a list of customers that do business with Amazon. We have customers in all kinds of areas, starting from industrial, healthcare, inventory tracking, smart buildings, and so on. So you see here a list of applications, and IoT is basically everywhere, and this is also what we are supporting. We support bespoke design so that you can optimize your design to match the needs that you have in your industry. Amazon offers a set of FreeRTOS libraries. They provide connectivity to the Amazon cloud services. This includes also, for example, things like Greengrass. The cloud connectivity is easy on microcontrollers. The software stack offers security, so you have actually a secure data communication, and also update over the air, and code signing is possible with this library set. The Amazon also offers an SDK. This is the C SDK, which enables you to connect microcontrollers basically using the same feature set as I have explained before. The SDK is OS agnostic and is actually the same code as the Amazon FreeRTOS library, so you have the same capabilities, and it's easy to integrate, and the demo that I will do is basically based on the Amazon SDK that we run on top of generic interfaces, of generic network interfaces. So now the section develop endpoints with Cortex-M microcontroller starts. As I said before, this slide shows the Cortex-M processor portfolio that we have today. Arm has been very successful with the microcontroller portfolio. We have shipped 52 billion microcontrollers up to date. And the range starts with the Cortex-M0, M0 Plus, M23 up till Cortex-M3, 4, M7. We have introduced a while back ago the Cortex-M33, which has also security on board. And new this year is the Cortex-M55, where we have added Helium instruction set. This is a vectorized instruction set. And this processor can also be combined with the Ethos U55, which is a neuronal network processor for machine learning. So this is the portfolio of processors where you can actually use the software stack that I'm talking about. The IoT devices are all different that we are addressing. We have already touched this in the first slide where we have talked about the various industries, and so are the endpoints very different. You find all type of endpoints from thermostats up till fridge, up till Fitbits, so fitness trackers, all type of stuff can be connected to the internet. We estimate actually that we will have 1 trillion devices connected to the internet by 2035. So this is an industry estimation. And this is an incredible high number. Therefore, I break it down also to help me understand the number better. What this really means is that we have in 10 years, every year, 10 million units on 10,000 bespoke designs. So we need to make the software development for IoT really easy to allow 10,000 different teams work in parallel on very different designs that are all cost optimized, as the high unit quantity implies that you will look for cost optimized solutions. Of course, not every device runs in 10 million, so we need to support a diverse range of developers, also developers that have a much lower quantities than a million. This slide shows a simplified view to the software building blocks that are required for IoT endpoints. We start here with the device board hardware abstraction layer. This is the configuration for the hardware specific part of your device. It configures the processor and the peripherals. On top of this HAL, typically you run an FreeRTOS kernel. This gives you the threat and resource management of your system. Then you have a secure network interface, which is the connectivity to the actual internet. You can implement this with various technologies. Then you have a cloud connector. This implements the protocol interface to the cloud service provider. And finally, a user application which implements the bespoke functionality of endpoints. Combined with security, this gives you an IoT endpoint. Security can run on a secure processing environment. This could be an external device, a secure element, but we have a solution based on TrustZone, which implements the security directly in the same microcontroller, so we offer diversity. What is also important to understand is that this software typically comes from different vendors. So the network interface is provided by the radio or interface provider, maybe also by the device provider or by a second party that delivers TCP/IP stacks. The cloud connector typically is provided by the cloud service provider as it implements specific functionality for the cloud service. Of course, the FreeRTOS and device board may come from a silicon vendor, so that you have actually the challenge to combine different software building blocks effectively. And to allow this, we have developed the CMSIS-Pack system. Ultimately, we want that the user can focus on his user application so that he can implement the bespoke functionality that is required for his device. So we try to make it really simple for the user so that he can focus on the application. Let me talk a little bit about the CMSIS-Pack system. What we show here is how CMSIS-Pack frames software components. So CMSIS-Pack basically uses software libraries or source code and specifies this software libraries and source code with an XML information. So there's an XML file. This XML file adds information like version and history information, license information. It defines the API. It can also relate to documentation. It then specifies the source files, and some of the source files may actually be configuration files. And then it also defines the requirements to other software components. The CMSIS-Pack system has been implemented already by various IDEs. You see here a list. We have it in Arm DS, we have it in Keil MDK. IRR has it implemented in EWARM. We have also an open source implementation for Eclipse that has been taken by several silicon vendors, and also ST has an implementation in CubeMX. The software components are framed in packs, and there are several web portals where you can actually get information about these packs. We have also now new open source command line build tool for the CMSIS-Pack system, so you can actually build this type of applications also with a CI system. Let me talk a little bit more about the API definition, as this is a common problem in the industry to have consistent API headers, and the CMSIS-Pack system therefore has a way to define a central API definition that comes with the software component and can then be referred by various implementations. This does not necessarily mean that the API definition needs to stay the same forever. You can actually involve it. We are using semantic versioning to define the version number, so you can define whether you have actually new functionality in the API header, or whether you have only bug fixes, or if the API header is completely inconsistent, so that you need basically new implementations. And the central API definition helps you with that, and the CMSIS-Pack system checks for consistency, so that when you have actually software components that come from different packs but refer to an API, can check that the API definition is actually suitable. An example for such an API definition is the CMSIS driver pack that implements various generic Flash, Ethernet, and Wi-Fi drivers that are all compatible with the CMSIS driver API, which is defined and maintained in the central CMSIS-Pack, where we deliver all the standard CMSIS software components. So this is a very important attribute of the CMSIS-Pack system to offer a central API definition. This slide shows actually various ways to connect to the internet. So we have on the slide 3 different ways to connect to the internet. One is via a Wi-Fi CMSIS driver and external Wi-Fi shields. You can also have on-chip Wi-Fi solutions, so this is not necessary to connect via UART or SPI. We have several Wi-Fi shields supported. So you can directly connect via an IoT socket to a Wi-Fi shield and run the TCP/IP stack in the shield itself, in the Wi-Fi chipset itself. The other way is to use wired Ethernet. This is here shown with MDK middleware or Lightway IP, which is an open source alternative. The MDK middleware has the option to actually work also with Wi-Fi. So you have a dual interface mode where you can have wired Ethernet or Wi-Fi Ethernet. And this is the diversity that you can see here. And of course, going forward, we will enhance that and improve the connectivity of the solution. Today, we support Wi-Fi and wired Ethernet via various means, and we connect to different set of cloud vendors. So you see here the list. This includes the AWS solution, also Azure and IBM, and the Google Cloud Platform and the Arm Cloud Platform. The security is implemented with Embed Crypto, but there are also other solutions that can be used to implement security if, for example, performance or space constraint designs are there. The managed runtime environment on this slide shows how you actually manage the software components of your application. We give with dialogues the flexibility to choose via easy-to-use interfaces. Here you see the selection that are possible with Wi-Fi. So you have the option to implement a custom interface, but you can also use ready-to-use software components for different Wi-Fi chipsets, as shown here in this slide, also with different interfaces. In this way, you select actually the software components for your application. These software components are then brought into your project window of the IDE, which is shown on the right side of the slide. And you see the clear relationship between the software components that comes from software packs. This is indicated with this green Lego stone here, compared to your actually user code. And what also the system takes care of is that the user workspace is not polluted with ready-to-use software components. So the ready-to-use software components are actually externally referenced, which also allows you to update easily packs. All you have to do basically is to download a new version of a pack, and then the system takes you to the configuration process, outlines when there is incompatible configurations and the likes. So this is taken care of by the various IDEs and the CMSIS-Pack system. And actually shown here, so you have ways to update drivers. You can download new versions. You can also, when your design is finalized, you can specify fixed versions. So you can then selectively update the components of your application, which is very important for the product lifecycle management, where you probably want to fix a specific bug that is already released in a new software pack. And in this way, you can pick and choose the software packs that you want to use in your actual application, which is important for the product lifecycle management. Once the application is completed, you connect to the cloud. I will show in a minute how to connect to AWS cloud. You have then various debug views in the IDEs. We show here a simple printf debug viewer. And of course, in the AWS portal, the communication is also reflected, so you can actually see how your device communicates with the cloud vendor, and you can verify in this way the correct operation of your application. This shows the complete software structure of the application that I will demonstrate in a minute. We have device configuration, so this configures the device setup. On top of the device configuration, which also includes the SDK of the silicon vendor, we run then the CMSIS drivers. There is an VIO driver for virtual I/O. This is useful for demo examples where you want to actually interface to your evaluation board peripherals. But VIO, as the name indicates, has also a virtual mode, so you can switch off the actual interface to the board peripherals and run it into your customized production hardware. So these are the components of the board I/O layer, and then we run in a cloud layer the actual internet connection. This is the IoT secure socket interface with a TCP/IP stack or Wi-Fi interfaces, and then a cloud connector, and on top of it, the application code. What's important is the device configuration is done via the silicon vendor tools. So there are various configuration tools available in the industry, depending on the silicon vendor that you are using. For ST, it's, for example, STCube-MX. Other silicon vendors have a similar tooling where you can graphically configure the pinout of your device, configure several aspects of the peripheral. You can add specialized peripherals that you are going to use in your application code. So you have in this system the full flexibility. And for security, you can use the Trusted Firmware M, which implements crypto and storage services. We are working also on secure boot methods so that you have actually the complete set of software components that are required in an IoT system. We have several reference examples, but I will explain this in a minute. What's also important is that once you have configured your system, that you have means to verify the configuration. This here shows the CMSIS driver set that we offer. We have different drivers depending on the device that you can set up and configure. The drivers are here to connect to middleware. You see this here in a different software pack. There are various middleware that connect, for example, to Ethernet. We have Lightway IP implementation or MDK middleware. Same applies to USB file system and graphics interfaces. This also only shows you an example. Then you have the option to validate the driver implementation. We offer here a driver validation pack that actually connects to the same configured drivers, and you can then check if the implementation and the configuration of these drivers is correct. This is important because we offer you the flexibility to reconfigure properties of these drivers, so you can use different I/O pins. You can also use different features, for example, DMA. And depending on the features that you have selected, you should verify that the driver configuration that you have chosen is actually working. And here we help with a driver validation pack. This is also extended to validate the Wi-Fi driver, so you can use this pack also to validate the Wi-Fi implementation in your system. So let me summarize. Here we show the complete range of CMSIS components. They are actually delivered in the CMSIS-Pack. We have a CMSIS-RTOS interface that is implemented via FreeRTOS and RTX, runs on top of CMSIS Core. We have various CMSIS drivers, which I have already explained in the previous slides. Then we also offer DSP and neuronal network libraries. They are required for machine learning. So this is the set of standardized software components that are part of CMSIS. You can extend this with device-specific peripheral interfaces that implement, for example, the interface to device-specific middleware, and then basically use this in your application code. So the benefits for you as a software developer is we offer unified software interfaces that actually are implemented across a diverse range of devices. When you change your device, you have a reduced learning effort. It is RTOS agnostic in the form that you can actually change the RTOS kernel as needed. There are also several other RTOS vendors that are offering an RTOS 2 abstraction layer. We offer for this system project and code templates, a consistent API for communication peripherals, so that you can actually use standardized middleware. We have for the IoT kits several reference examples available. This is shown on keil.com IoT. You can pick reference examples for various evaluation boards. We have here a list. This includes the Arm Musca board, which is an Arm test chip, several NXP and several ST chips. We are going to work with the industry to extend the offering on the evaluation board so that you have actually more reference examples available that you can then simply download and explore. This download page is currently for Keil MDK. So when you download such an example, you can take it into Keil MDK, but we are working on vendor neutral project format, which allows then also to take it into other IDEs so that you have not a specific IDE that you need to use to work with the IoT devices. And now I'm going to demo that. For the demo, I'm actually using an ST Nucleo board. So we will show you an example project on an STM32 Nucleo board. And we have downloaded an example project from keil.com IoT. The example runs on the STM32L5 that has some cool new innovations. It is the first microcontroller from ST with Cortex-M33 and Trust Zone. And it gives you a secure processing environment on a single processor. The alternative solution for that would be an off-chip secure element, but compared with this, a Trust Zone enabled device reduces the overall system cost, and even the program executes faster and consumes less power. The example project on the Nucleo board is based on the ST-HAL, our CMSIS framework and IoT cloud interfaces that I have explained before. It connects in this configuration to Amazon Cloud using a Wi-Fi internet communication, and we execute the classic MQTT demo from AWS. In the debugger, you can see each step of the data communication, and of course, the data are also visible in the AWS MQTT console. Now let's explore this project a bit and see how it's composed. In the secure mode, use Trusted Firmware M. This software is the security foundation, and ST already has achieved the level 2 PSA certification, which gives you as a user the confidence that security is implemented and verified. In the non-secure part, we run a CMSIS-RTOS, a secure Wi-Fi network interface, the IoT device SDK from Amazon as cloud connector, and a user application, the MQTT demo. All the private keys and root of trust information is stored in a secure space. It is not accessible from the non-secure part. In case that a firmware attacker breaks into the system, there is therefore still no way to access this secure storage. For any other STM32 device, you can select and configure the chip pin out and the peripherals using CubeMX. So therefore, you have the full flexibility of CubeMX to define your bespoke pin out in your final hardware design. And in case that you really need a different configuration for the trusted firmware, for example, because you need more secure storage, we support this with CMSIS-Zone. With this utility, you can change the security properties and the memory layout of the complete system. And the software that we use here in this demo is all open source, so you can adopt it to your needs. And we are just working on a tutorial that helps you to get started quickly. So in a couple of weeks, you can actually have a step-by-step introduction on how all of this is done. So let me summarize what we have discussed. So ARM takes an holistic view to the development cycle of IoT endpoint devices. We do this because we envision that we will have a lot of developers that are going to implement IoT endpoints. CMSIS provides the software interface standards that ensures the interoperability of the software components. We have invested into a platform security architecture to ensure ground-up security in these devices. You can take a look to arm.com PSA for that. And on Keil.com IoT, you can find the various IoT clients with the reference examples that I have explained before. So you can download the reference examples for various evaluation kits, and going forward, we will increase the number of supported boards and diverse microcontrollers that we expose here. So this is the end of my presentation. I would like to thank you for your attention, and we are now open for Q&A. So if you have questions, please raise them now.